Okay, so for part 3 of homework 6-5 here, hopefully get through questions 6 and 7. And as I mentioned in the previous parts, these are two very challenging questions. So obviously please make sure you're paying attention as you go through these. Definitely attempt them first, but don't feel bad if you have to consult the key here a little bit to get through them. But anyway, let's get to it. So question 6, you have two stars in a binary system. They do have, however, different masses. So we saw in class what to do if they have equal masses. A little bit different if they have unequal masses, right? They're separated by this distance given here. What is the period of the system's rotation in years, in an Earth year that is, and then what is the speed of each star as it rotates around the center of the mass for the system? So one part that is a little bit tricky about this is maybe at first you're not going to think that they both rotate at the same rate, but they actually do. It takes the same amount of time for both of them to rotate around the center of this system. So let's get a feel for what this system looks like. So again, I've got two different masses. One of them is a little bit larger, so one of them is 6.0 times 10 to the 30th, right? And then one of them is a little bit smaller, so 2.0 times 10 to the 30th, right? So if I'm thinking about this, one of the key concepts here is you do need to be pretty comfortable thinking about the center of mass, right? I know that the total separation between these two, the total separation between those two is 2.0 times 10 to the 12th. But I want to think about where would the center of mass for the system actually be. Well, in general, I know it would be closer, right, to the heavier object. But I want to find out exactly where. I want to find out exactly how far from the larger star is it and how far from the smaller star is it. Right? So that does go back to how do we calculate the center of mass. Well, as we've seen before, right, the center of mass is taking my first position times mass 1 plus my second position times mass 2, and then dividing it by the total mass of the system, right? So m1 plus m2. In this case, they don't necessarily give us initial positions, but I can just choose one of these to be 0 and choose the other one to be the full distance away, right? So maybe I want to choose the 6.0 times 10 to the 30th. Maybe I want that to be at a position of 0, right? Then over here, the 2 times 10 to the 30th, that would be at a location of 2 times 10 to the 12th. That's the total distance, right? So 2 times 10 to the 12 meters away. So as I plug in to find my center of mass, I've got again my first mass, my heavy mass, times 0, so really that one doesn't matter. And then plus my second mass, so 2 times 10 to the 30th. And then that whole thing times its position of 2 times 10 to the 12th. So obviously we can calculate that number. And then divide that number by the total mass of the system, which would be 2 plus 6, so 8 times 10 to the 30th. Right? So as I calculate this, what that tells me then is the center of mass is, when I calculate it, ends up being 0.5 times 10 to the 12th, or in other words, 0.5 times 10 to the 11th, right? Or excuse me, 5 times 10 to the 11th, 5.0 times 10 to the 11th. But that tells me how far away it is from where I define 0 to be, right? So again, 0.5 times 10 to the 12th meters away from where I started. So the center of mass of the system here is 0.5 times 10 to the 12th away from the heavier sun. So then that means it's a remaining distance of 1.5 times 10 to the 12th, right? If I just subtract 2 times 10 to the 12th minus that, that tells me how far it is from the smaller sun. Which again, if you kind of pause for a second, think about it, right? We know that the center of mass should be closer to the heavier mass, and it should be further away from the smaller mass. And in fact, it is, because this is 3 times as large, it is 3 times closer, if you will, to the heavier mass. So hopefully both of those numbers make sense as we find it, right? But anyway, I found the position for the center of mass, right? So why is that important? Why does that matter? Why do we need to do that for this particular question? Well, the reason we need to do that is because as I look at this system, right, there's not actually an object at the center of mass. So as these two stars, as these two suns, if you will, orbit around the center of mass, they're both going to follow relatively circular orbits here, right? So the heavier mass is going to follow a tighter circle. The smaller mass is going to follow a much larger circle. But they are going to both follow these circular orbits. But again, I told you that the period for these orbits is going to be the same. And if you think about the period formula, the period equation that we know, right? We know this one from the past for circular motion, right? If you were looking at this, how in the world would they be the same if they're different radii? And the key for that is, where does this equation actually come from, right? I can't use this equation anymore because I have to understand where that equation actually comes from. Well, that equation comes from really boiling it down to the relationship that if something's moving in a circle, I have to have a centripetal force. And what's providing the centripetal force? Well, the only thing providing the centripetal force for either one of these is the mutual force of gravity between them, right? That is the only force that's pulling them towards the center of the circle. So we start with the same relationship we're used to. The centripetal force equals the force of gravity. So, if you will, I'm going to break that up. mv squared over r, right, my centripetal force, equals g m1 m2 over r squared. Here's where we have to be careful. These are not the same r, and let's think about why. So I'm going to focus on, for a second, I'm going to focus on the larger star, which is closer, right, to the center of orbit. So the centripetal force, when we're dealing with this equation, the centripetal force is based on the radius of the circular path, right? Well, the radius of the circular path for the larger object would just be the 0.5 times 10 to the 12th meters that we defined before, right? The r that we use for the entire gravitational equation is not 0.5. The r that we use over here is actually the total separation, right? It's the total separation between the two stars. So the r over there is actually the full 2.0 times 10 to the 12th. And again, that becomes the key to this question. As soon as we make that realization, I think and hope that this question is not as bad to get through, right? So what can I do? Well, I can still cancel out the mass of the heavier planet in this case, because again, I'm choosing to work with the heavier planet, right? So I can still cancel out the mass of the heavier star, I should say, not planet. But anyway, I can do that. So I get v squared over r, keeping in mind that this is, I'll call it radius 1, it's the shorter radius then. And then over here I've got g m2 being the mass of the second star, and then r2 I'll call that, which would be the distance to the second star. So at this point I've got enough to where I could actually partially answer part B, right? Part B asked me to find the velocity of that one. I could go ahead and do that. I'm actually going to go ahead and solve it generically first, and what I mean by that is I'm going to solve for the velocity. So velocity squared would equal g times m2 times r1 if I multiply that over, and then divided by r2 squared, right? So this would be my velocity, and then obviously I could square root both sides to get my velocity by itself. And then to find the period, well, the period is just taking advantage of velocity equals 2 pi r over t. Again, the question I want you to think about, though, is which r is this? Well, again, this is coming from the circle, right? This is coming from the radius of the circle. So once again, for the heavier mass, that would be the 0.5 times 10 to the 12th. That would be my r1 that I've used here, right? So if I solve for this, if I plug in the square root there, if I square root both sides, I've got v equals the square root of gm2 r1 over r2 squared, and then I substitute that value in up here for the velocity, keeping in mind that this is r1, and then I solve for the period. And so what you get is a little bit of a mess, right? A little bit of a mess in solving for this period, but I'll go ahead and try and do that both generically and then help you substitute numbers in as well. So like I said, I know a longer part of this question here. Some of you guys feel free to jump ahead and check your answer, but I will continue to work this out. So plugging that in, right, substituting that in, and then solving for t. So I'm going to multiply both sides by t and then divide by the velocity, so divide by this whole thing. So I get 2 pi r1 and then all over the square root of g m2 r1 over r2 squared. I'm going to go ahead and square everything to get rid of the square root. So for just a moment I'm going to square everything. So I get t squared equals 4 pi squared r1 squared all over, I get a little bit of a complex fraction here, but g m2 r1 divided by r2 squared. If I look at this equation, obviously it's a little bit tricky to simplify it, but I do have an r1 on top and an r1 on bottom, so I can cancel at least one of those out. And then obviously if this is in the denominator, if it's a complex fraction, right, I can move that up to the top if I flip multiply. So I end up with t squared equals 4 pi squared r1 times r2 squared all over g m2. Right, so like I said, a little bit of a mess, and obviously the tricky part here is breaking up which variables are which. The reason that I do want to leave this equation generic is because this equation actually will work out to give us the exact same answer no matter which star I choose to work with. And what I mean by that is if I choose the heavier star, then I'm going to use the radius 1 as being the distance to the center of the star system, right? So that would be the 0.5, and R2 would be the total 2.0 times 10 to the 12th. If I choose the heavier star, then I use the smaller star as the mass over here, right? So I'll go ahead and show you the numbers I substitute in for that calculation. So 4 pi squared, again, the radius for the heavier star would be 0.5 times 10 to the 12th because that's the radius of its circular path. But the total distance between the two stars is still 2.0 times 10 to the 12th. So I'm using those measurements, and then on bottom, obviously 6.67 times 10 to the negative 11th, and then I'm using the mass of the smaller star because that's the mass that we're orbiting around, right? The heavier star is, if you will, orbiting around the smaller star. So I'm using the 2.0 times 10 to the 30th for that measure. Okay, so if I calculate this, if I calculate this whole mess, you end up getting a measurement when I do square root both sides, so I'm going to go ahead and square root both sides as well. You get a measurement of 769337587. I know that is not very numerically correct, but that's how many seconds, right, the period would be. It does ask for the period in terms of years, so I need to figure out how many seconds are in an Earth year and then divide this by that number of seconds. Well, I will trust that you guys can convert the number of seconds in a year. I am using 365.25 days, so as I calculate this number, that's what I'm getting. But I have 31,557,600 seconds in a year. So when I divide that, I get my period to be 24.4, about 24.4 years, right? So if I use the heavier mass, the heavier star, I end up getting 24.4 years once I convert that to Earth years. If you use the smaller star, right, if you choose to use the smaller star to work with instead of the heavier star, let's just think about what would change, right? So the only thing that would change would be I would use the distance to the center of the smaller star's orbit, which would actually be the 1.5 times 10 to the 12th, right? Not the 0.5, but the 1.5. And then this measurement would stay the same. But this measurement down here would now be the smaller star, which is orbiting around the larger star, right? So I would use the mass of the larger star, so 6.0 times 10 to the 30th. Well, look at the only measurements that changed, right? Isn't the only thing that I changed was I multiplied this by 3 and I multiplied this by 3? And obviously, when I multiply the top and the bottom by 3, it doesn't actually change anything. So the whole point, the moral of the story is I end up getting the exact same period. So even though these two stars do orbit at a different radius, they do take the same amount of time to orbit. It's a very big conclusion, and like I said, I know this question is very tough. We will talk about this a little bit more in class just to make sure everybody's okay with it. But it is a very big conclusion for us. Anyway, moving on to part B. And I am going to try to make part B pretty quick and easy here for us. Because as soon as we find the period, if I want to find the orbital velocity of each star, so I'll call one the velocity 1, and let's just say that's the smaller star. If I want to do that, I'm just going to do 2 pi r, the total distance it goes, divided by the period. Right? So the smaller star would go 2 pi times the radius of 1.5 times 10 to the 12th. Right? And then dividing that by the period, keep in mind I do want the period to be in seconds, and so that's why I'm going to use this measurement that I wrote down up above, but using that number there for obviously my time, for my period. So when I calculate that, when I find the velocity of the smaller star, that ends up being about 12,250, if I round it off a little bit here, meters per second. So that's the orbital velocity of the smaller star. And then the orbital velocity of the larger one, I use the exact same equation, 2 pi r over t, because I know both of those measurements. The only thing that I change here, right, is instead of 1.5, I'm using 0.5 because it doesn't travel as much of a radius, right? It doesn't travel as far. Using the exact same time, though, and then calculating that measurement, I get about 4,080. So about 4,080 meters per second. And again, make sure that answer kind of makes sense. The first star, the smaller star, would have a larger circumference to go, but it takes the same amount of time, right? So it should have to travel faster in order to cover more distance in the same amount of time. Larger star goes less far in the same amount of time, so it goes a little bit slower. Okay, so obviously question 6 took me almost the entire 15 minutes to get through. So definitely a bit of a doozy here. Definitely some key concepts as well, though. So please make sure you do look through this question. If you have further questions, come find me so I can help you out with it. it is an important problem for us to think about.